Hello everyone, my name is Tom Rice-Blatticus,
My name is Krista Morocco.
And my name is Trini Grinspan.
and we're here to talk to you about interference. Today we are going to be presenting our electromagnetic interference experiment, also known as EMI. Let's first start off with some background information. At the heart of this experiment, we want to generate interference in some kind of cable. We can induce a voltage across a coiled cable, which is denoted as N2, by exposing it to a time-varying B field. We can also generate this B field by inducing a current across an inductor, denoted as N1, in our interference generator. A static B field will not generate a voltage across a wire. Rather, we must use an alternating B field. We accomplish this by creating a sine wave current through the inductor through the use of an LC oscillator. This circuit will charge up the inductor to a predetermined current, then allow the inductor-capacitor loop to oscillate at their natural frequency, producing a B field with the same frequency.
Next, we are going to get into our circuit explanations. Essentially, we have three pieces in our project. We have a sound card, an amplifier, and of course the interference generator. The sound card is what transmits the signal, in this case our music, and the amplifier receives the signal and amplifies it. The interference generator does exactly what it sounds like it does. It interferes. Here we see the schematic of our interference generator. The interference generator is essentially just an LC circuit. In the circuit, there's a clock that turns on and off, which in turn causes voltage to go high and low. When the clock pulses high, or there's voltage going through the circuit, current charges up the inductor. When the clock makes the voltage go low, the inductor will discharge, which causes a voltage to be generated to combat the decrease in current, which then charges up the capacitor. This capacitor discharges, and that discharge charges the inductor. The cycle continues where the inductor charges and discharges, and then the capacitor charges and discharges. This creates the frequency. The frequency is what drives our time-varying current, which will cause a time-changing B field, as we saw in Ampere's law. This time-changing B field causes for a time-changing flux, which induces a voltage by Lenz's law. Now, in addition to our circuits, we have different types of wires, which will be our coils that we induce a voltage on. We have a copper wire that allows the analog signals to be transmitted, and we have an optical fiber cable that allows digital signals to be transmitted. In addition, we will also be exploring digital signals going through a copper cable to see the effects on interference.
Let's start by showing how potent this interference generator is. I'm now going to measure the voltage induced across this cable. On screen is the oscilloscope view showing the induced voltage. As I bring the circuit closer to the cable, you'll start to see a measurable voltage. This circuit can create damaging voltage swings across this wire.
So now we'll start out with the analog signal with the copper wire. Here's the interference generator we will be using. I will be bringing the interference source close to the coiled cable, which will increase the B field, and that also increases the induced voltage, which in turn increases the noise in the cable. The circuit is vulnerable to external interference, even using the shielded copper cable. And that's why you can hear the 5 kilohertz frequency. Now we're going to switch to the optical fiber cable. Let's see if there's any audible interference. As you can see, the audio signal is well protected because the fiber optic cable is not conductive. Additionally, the signal has been converted to a digital one, which also helps mitigate signal interference. So, as Trini mentioned earlier, the copper wire can also be used with a digital signal. Let's see what happens when we use the interference generator now. So this horrible static sound occurs instead of the 5 kilohertz frequency tone because the interference generator is causing there to be lost bits during transmission. So from this demo, we have learned 2 techniques to reduce signal interference: switching the analog signal to a digital signal, and then using a fiber optic cable instead of a copper one. So let's move on to some applications of this experiment. All electronics are susceptible to signal interference. Some common examples of electronics that we use in our everyday lives that have to mitigate signal interference include radios, phones, and televisions. Some more specialized examples include medical equipment, audio equipment for live performances, observation equipment for tracking weather and astronomy, and electronic warfare, often in the form of radio jamming or EMPs.